Hi, AB Stats. Today we're just going to do a quick review of Lesson 9.1, Day 1. And Lesson 9.1 in your textbook is about significance tests and the basic ideas. So the learning targets today are to state appropriate hypotheses for a significance test about a population parameter, interpret a p-value in context, and make an appropriate conclusion for a significance test. Now, this is an activity that you should have completed in class. We're just going to go through and we're going to summarize what the main ideas are. So, a significance test is a formal procedure for comparing observed data with a claim. The claim is the hypothesis, whose truth we want to assess. We express the results of a significance test in terms of a probability that measures how well the data and the claim agree. Significance tests will deal with claims about a population. It will ask if sample data gives good evidence against a claim. If we were to take many random samples and the claim were true, we would get a result like this a certain percentage of the time. The basic idea is an outcome that would rarely happen if a claim were true is good evidence that the claim is not true. So, important ideas is developing your hypotheses. We have our null hypotheses. It's what a person claims to be true. We'll use this H sub O to denote our null hypotheses. It is also called H naught. When we write our null hypotheses, we will always use the equal sign and set it equal to the parameter. So we'll have H naught, and if our parameter is the mean is equal to the null value. Or if our parameter is P, it'll be equal to our null value. It is the claim about the parameter that we're trying to find evidence against. So we're always trying to find evidence against our null hypothesis. Our alternative hypothesis is the claim we suspect is going to be true instead of the null hypothesis. We can have it one-sided where we write it and we use greater than or less than with our parameter. Or it could be two-sided where we say it's not equal to our null value. Okay, so the alternative hypothesis is a claim about the parameter you're trying to find evidence for. It's what we think is probably true. So now we're going to interpret what a p-value is. Okay, so the probability, this is what a p-value is, it's the probability that we would get this sample result or one more extreme, either less than or greater than, depending on the direction specified by our alternative hypothesis, just by chance if your null hypothesis is true. So again, when we do a p-value, we are making the assumption that the null hypothesis is true, and we're trying to figure out what's the probability that the sample result would occur, or one more extreme, just by chance if it's true. The smaller your p-value is, the stronger the evidence is against your null hypothesis. So p-value, you want to understand what the definition is. It's a conditional probability. It's the probability that your sample data occurs given your null hypothesis is true. Once we have our p-value, we can make conclusions. We either do or do not have convincing evidence against the null hypothesis. That's the conclusions we're trying to make. So if something is significant in statistics, we don't say that it means important. In statistics, to be significant means it's likely to not happen by chance. So if a p-value is less than alpha, alpha is going to be our significance level. Okay, the level, anything below that, we're going to start to think that, hey, this didn't happen. This is really unlikely to happen by chance. So our significance level, if your probability, your p-value that you find is less than alpha, it's significant, meaning there is evidence against the H or the null hypothesis. So if a p-value is less than alpha, we're going to reject our null hypothesis because we have evidence against it. If our p-value is greater than alpha, we're going to fail to reject our null hypothesis because the evidence is not convincing against our null hypothesis. One thing we never want to say is to accept the null hypothesis as true. You will lose points for that because we are not proving that it's true. We just don't have enough evidence against it that we can reject it. So if the problem doesn't tell you what significance level you should be using, in general, you'll use 5%. Okay, so if it tells you what significance level to use, great, but if not, you will use 5% as your significance level. So why don't you pause the video and try the check understanding, and then come back and let's see how you did. Okay, so we have this problem here about the calcium intake, and they recommend that calcium intake for teenagers be 1,300 milligrams per day, but the NIH is concerned that teenagers are not getting enough calcium. So for our null hypothesis, we're going to say that the mean intake is equal to 1,300 milligrams, but alternative hypothesis is that we think that the mean intake is probably less than 1,300 milligrams. Again, when you state your hypotheses, you have to state what the parameter represents, that the mean is the true, mu is the true mean daily calcium intake of teens. So they go through and they collect data from 20 teens, and they find that the mean intake for that sample is 1,198 milligrams, and the standard deviation is 411 milligrams. They run a significance test and obtain a p-value of 0.41404. Explain what it would mean if the null hypothesis to be true in this setting. Well, here is our null hypothesis. So we would say if our null hypothesis is mu equals 1,300 milligrams is true, then we interpret that as this is the mean daily intake in the population of teens is 1,300 milligrams. It's just interpreting what it would mean. For 3, interpret the p-value. So again, a p-value is a probability that your sample data, given that the null hypothesis is true. So we're accepting that the mean value is 1,300 milligrams. So our p-value is 0.1404. So we're going to say there is a 0.1404. That's about a 14.04% chance. Probability of getting a sample mean of 11.98 milligrams or less. Again, it's or less because it's in the direction of our alternative hypothesis, and our sample mean was 11.98. So there's a 0.1404 probability of getting a sample mean of 11.98 milligrams or less purely by chance, given conditional probability that the true mean daily calcium intake of teens is 1,300 milligrams. Again, you can write that in reverse order, saying if it is true that the mean daily calcium intake of teens is 1,300 milligrams, then there is a 0.1404 probability of getting a sample mean of 11.98 milligrams or less, purely by chance. Typically, I tend to write it in forms of the given. I give the probability of the sample data given that the null hypothesis is true. But either way is correct. What conclusion could you make at a significance level of 0.05? Well, our p-value, 0.1404, is greater than our significance level of 0.05. So that's not significant. We don't have enough evidence now against our null hypothesis because it could happen by chance. So we are going to fail to reject our null hypothesis because our p-value is greater than our significance level. Then we state we do not have convincing evidence that the true mean calcium daily intake of teen population is 1,300 milligrams. All right, so try the next one on your own, pause it, and come back and see how you did. Okay, so we have Mike who is testing a new 7 iron, and we have his hypotheses over here that the standard deviation is 15 yards, but the alternative is that it is less than 15 yards. So our p-value is 0.002. Interpret the p-value in context. There's a 0.002 probability of getting a sample standard deviation of 10.9 yards or less, because that's our sample data, purely by chance, given that the true standard deviation of the distances Mike hits the golf balls with the new 7 iron is 15 yards. Now, if your significance level is 0.01, what conclusion can we make? Well, we take a look, we compare our p-value to our alpha. In this case, our p-value is smaller than our alpha. When p is smaller than alpha, it's significant, meaning that that probability is unlikely to occur by chance, so we're going to reject the null hypothesis. We have convincing evidence that the standard deviation with the new 7 irons is less than 15 yards. Okay, that's just a quick summary of section 9.1.